Welcome back, and in this section of the course we're going to talk about error metrics. In this lecture I'm going to give an overview of what we're going to discuss in this section of the course, and so let's introduce error metrics. So what are error metrics? Error metrics, sometimes also known as error measures, are ways to summarize our forecasting errors into a single number so that we can measure the accuracy of our forecast. So here we have a time series, and we have some actuals, and we have our forecast, and this is our forecasting horizon. And so the difference between the actuals and forecasts gives us our forecasting errors, and they can be positive or negative depending on whether we over or under forecast. And so we would like to summarize these forecasting errors into a single metric. Now, because these forecasting errors can be negative and positive, if we were simply to take the mean of these forecasting errors, the over forecasting and under forecasting might cancel each other out, and we think we will have a good forecast when we don't. So typically the first thing we do is find a way to make the forecasting errors positive and then average them. And so this is how we encountered the mean absolute error. We took the absolute value of our forecasting error and then took the mean of those absolute errors. Alternatively, we could also square the error to make it positive, and so then we could average the squared errors, and this gives us the mean square error. Now the only issue with this is the scale of the mean squared error will be different to the scale of the time series. If the time series is measured in dollars, then the mean squared error would be measured in dollars squared, and so it's typical to take the square root of the mean squared error so that we get a metric which is on the same scale as the original time series. And this creates the root mean squared error. And so now here we have two metrics with which to measure the accuracy of our forecast. We can ask, which forecast is better? Imagine we have our time series and we build two different models. We can then measure the mean absolute error for these two different models and ask which one is better. And then we will pick the model with lower error as the one to use. So we can use error metrics to help select our models, features, and hyperparameters. They are also used when we are reporting and monitoring our forecasts. So we're done, right? We can minimize our error metric and pick the best model. Well, it's not as easy as that. Let's look at this example. So imagine we have an intermittent time series, and so most of the values are 0, and we have the occasional non-zero values. Now we have model A, which has a mean absolute error of 3, and model B, which has a mean absolute error of 0.1. We might be inclined to say that this model has the lower error, and therefore is the one that we want to put into production. But what happens when we look at the forecast? We will see that the forecasts are all 0. Why is this? It's because minimizing the mean absolute error optimizes for the median. We will explore this later in this section of the course. And because the median of our training set is 0, most values are 0, we will end up forecasting zeros in our forecasting horizon. And so this may not be a very useful forecast if all we're saying is that for time series which have a lot of zeros, we will forecast zeros forever into the future. If instead we use the root mean squared error, we will actually get non-zero values for our forecast. And this is because the root mean squared error optimizes for the mean. We'll end up getting the mean of our training set, and so we'll forecast a non-zero value. Now, we will discuss this more later in this section of the course, but what this illustrates is that the properties of the time series and the choice of error metric can give very different optimal forecasts. And so we need to consider what our time series looks like and the properties of our error metric when deciding how we want to evaluate our model. Let's look at another example. Imagine we have two time series 1 and 2. The mean absolute error of time series 1 is 10. The mean absolute error of time series 2 is 100. Are we more accurate on time series 1 or 2? Naively, we might pick time series 1 just because we have a lower mean absolute error. But what happens when we look at time series 1? If we look at the scale, we can see that the average value of the time series in the forecasting horizon is roughly 20, and so a mean absolute error of 10 is roughly on the order of 50% of the average value of our time series. If instead we look at time series 2, we can see that the average value of the time series in the forecasting horizon is 1000 here, and so a mean absolute error of 100 is roughly only 10% of that average value. And so the forecasting errors on a relative scale are actually much smaller for time series 2 than time series 1. And so this demonstrates that the scale of the time series matters. This is important when we're comparing errors across multiple time series and if there is a change of scale within our time series, and this may be due to outliers or level shifts. And so we're going to discover that there are many different error metrics. So far we've discussed scale-dependent error metrics, which are based off of the standard base error, which is just the actual subtracted by the forecast, and from that we made it positive by either squaring or taking the absolute value, and then we can apply some aggregating factor like the mean or median on these errors. We will discover that there are scale-independent errors where we rescale this error to give us either a percentage error or a relative error if we were to rescale by the error from a naive model. And we also have what are called scaled errors, and this is where we rescale by the error in the training set rather than in the test set. And there are other error metrics which don't neatly fall into either of these categories. And we will find that each error metric has its own pros and cons depending on the properties of the time series and the use case. We will see that there are several factors which impact which error metric we should use, such as whether we have an outlier. Do we have multiple time series and the time series are in different scales so that some time series are a lot larger than other time series? Do we have an intermittent time series, that is, a time series which is count-like and has lots of zeros? Do we have a time series where we have trend, seasonality, heteroskedasticity, and this is where the scale of the time series increases with time, and do we have structural breaks? So here we have trend, we have seasonality, we have heteroskedasticity because the scale of the time series is increasing over time, and we have this structural break. And so depending on the properties of our time series, we will find that different error metrics will be beneficial. So in this section we will discuss what are the components of an error metric. We will discuss many different error metrics and their pros and cons. We will discuss when to use each error metric. We will show what error metrics exist for multiple time series. And in addition to measuring our forecasting accuracy, we will show how to measure our forecasting bias as well. And so I hope that's exciting, and see you in the next videos in this section of the course. See you then.